Hi. Okay. My name is Ema Iancuta, and together with my colleague Radu Chilom, we will present in-memory data pipeline and warehouse at scale using Spark, SparkSQL, Tachyon, and Parquet. Both of us, we are software engineers at Atidjo. Atidjo is a company that provides big data analytics and machine learning solutions. Atidjo worked with Hadoop for more than 6 years and then switched to Spark. And so we have been working with it for the past 2 years. In our free time, we build up a big data research community that focuses, that focuses on the technical problems that this field has and offers open source solutions. After this quick intro, we will describe our use case. We will speak about how to build a data pipeline with Spark. We will speak about our 2 open source projects, Spark Job REST Service and Spark SQL REST Service, codenamed JOS. There will be a few words about Parquet. We will briefly go through the benefits of using Tachyon. There will be 2 short demos also. So our use case is to build an in-memory data pipeline that will process millions of financial transactions that would be used downstream by the data scientists in order to detect fraud. First, we will need to ingest the data from S3 into Tachyon, cluster backed up by a cluster of HDFS. HDFS will be the underlayer file system for Tachyon. Then we will have to transform the data in order to fit the requirements of our data scientists. And in the end, we will want to build a warehouse that will allow to run interactive queries with SparkSQL. In the next part of our presentation, I will let Radu deep dive into the first challenges this use case brings up.
Hi. Next, I'm going to present you the first part of the in-memory data pipeline, which consists in 2 steps, downloading and transforming a large amount of data. As in-memory distributed engine, we've chosen Apache Spark. A few words about it. Spark is a fast and general engine for large-scale data processing. It was built around the concept of RDD, which is an immutable collection of elements partitioned across the cluster's nodes. Spark has a rich API consisting in 80 high-level operators, and on top of it, there's a stack of high-level tools, including MLlib and SparkSQL. For our use case, we want to download the data from an external source, a public S3 bucket named public financial transactions. Even if we are downloading for S3 in this use case, the things that I'm going to present apply to other external sources. So as you can see, the structure for this bucket is very simple. The scheme is in the scheme folder, and the data files are in CSV format and are divided into multiple data folders. The easiest way to get the data into our cluster would be to use the method whole text file that Spark Context offers. As input for this method, we have a regular expression containing 2 wildcards. The first wildcard will match all the folders inside the bucket, and the second wildcard will match all the files inside the folders. In order to transform from wildcards into file names, behind scenes, Spark lists the file's metadata. This is a problem because listing the metadata for a large number of files in an external source can take a long time. So in order to improve this, we can list the metadata distributed. So instead of listing all the files on the driver, as we did before, we can now get the folders list there, parallelize it, and get the metadata for the files inside each folder in a distributed way on multiple cores. Let's see the code for this. So as you can see in the first part, we're obtaining the folder list with the use of an S3 client, and then we are parallelizing the list. By the way, it's worth parallelizing only if the folder list is greater than 1, because if you have only 1 folder, then you will only move the computation from the driver to one of the workers. Okay, and then with a flat map, we're going to get to list all the files from the folders. By default, the parallelize method creates a number of partitions in our cluster that depends on your cluster manager. However, in order to fine-tune your jobs, you can specify the number of partitions by adding an extra integer parameter to the method call. As a tip, you will probably want to have the number of partitions as least as the number of available cores in order to fully benefit from our computation power. Okay, the download part is pretty straightforward. We're doing a map in which we're initializing an S3 client and we're downloading the file. The problem that might arise here is if you have unbalanced partitions. So we can end up in a situation similar to this, where the data is not evenly distributed among partitions. This happens because the default partitioner is a hash partitioner, and for the string data type, it doesn't always provide an even distribution. As you may know, the elements in each partition in Spark are processed by a separate task, so the real problem with unbalanced partitions are that while some of the tasks finish very, very quickly, the rest of the tasks struggle to finish. This leads to an increased overall time for your stage. Okay, a solution for this would be to rebalance our partitions by hashing on an integer index. We can achieve this by transforming the file name RDD into a pair RDD that would have as a key a unique index attached. Okay, so now let's see the code for this. As you can see, we can achieve this with the zip with index operator. And what this does is that it adds to each element of our RDD a unique index. Then we have to use a map operator in order to interchange the key and the value. And so the index ends up being the pair's key. After that, we want to repartition our RDD in order to shuffle the data around and balance the partitions. Please keep in mind that repartitioning your data is a fairly expensive operation because it shuffles data across the cluster. However, in some use cases, the benefit of repartitioning is much more greater than the penalty it inflicts. Now let's move to the data transformation step. Data cleaning is the first step in any data science project. In our use case, we have to remove the lines that don't match the structure and some of the columns that are useless for our analysis. Another thing we want to do is transform the data in order to have a consistent format. So we have two columns, both representing country codes. The problem is that one is in numeric format and the other one is in alphanumeric format. So in order to be consistent, we can join the transactions RDD with the countries map RDD, which is this, and change the value from the transaction from numeric to alphanumeric. The problems with joins in Spark, and also, I think, when doing Hive, arise when you have a skew in your key distribution. So, as you might know, all the values for a key have to be processed in the same task. So, if a key is very frequent, much more frequent than the others, the task that will process that key will take much more time to finish. You can spot the skew key distributions by looking at the summary metrics when running an action on top of your join transformation. So as you can see here, while 70% of the task finished in under 2 seconds, the maximum task took 17 seconds. Also, you may want to look into the shuffle read field, and you can see that there are very large differences. So when you can see this kind of differences in a join or in a group by, it's very probable that you have a skewed key distribution. We can achieve this transformation also by shipping our country code map to each worker in our cluster. We can do this with the broadcast operator, which takes your value and sends it to each node of the cluster. This method is suitable only if the data you are shipping to the cluster it's not that big, because it inflicts serious I/O penalties. As you can see in the code, after broadcasting the country's map, we can achieve our transformation with a simple map or flat map in which change the value. Now let's take a look at the metrics from running an action on top of this transformation. As you can see, the running times are now very close in range, and we can also say that about the input. So, yeah, when each task processes the same amount, the duration is only 7 seconds per task instead of having multiple tasks that finish in 2 seconds and one that runs in 17 seconds. Now I want to show you a chart with the running times with the running times of the both presented transformation versions. As you can see, the broadcasted map version is much more faster and it looks linear, while the join version looks exponential. However, this only applies when you have skewed key distribution. Now that we have implemented a downloading job and a transformation one, we have to run them. We can run them on top of Spark Job REST, which is a RESTful server that provides context management and job submission services. Spark Job REST is an open source server which we created in order to fix the inability to run multiple Spark contexts in the same JVM. This is a Spark core bug that still hasn't been fixed, and that also affects Uyala Spark Job server, from which, by the way, we've started, but facing the urge to run on multiple contexts, we came up with this server that, as a solution, spins up a new process for each context it creates. I'm going to show you a quick demo now. Okay, so this is the UI for Spark Job REST. It has 3 sections: context, jobs, and jars. In the context tab, you can see all the running context on your cluster. You can create one or you can delete one. A very nice feature is that we have managed the Spark UI ports in order to show it here, and also in order to give you a quick link to the Spark UI page where you can see all the tasks that have run on your context. In order to create a context, you have to provide a jar with your classes. So you can go to the jar section and upload your jar. As you can see here, I have 2 uploaded jars. One of them is S3 download job. I'm going to create a context and run that job. Okay, so in order to create a context, you should specify a context name. Let's say data download context, a jar. A nice cool feature is that here you can add multiple jars, and also you can provide HDFS path. So if you have your jar in HDFS, you don't need to download it and upload it to the server. In the parameters section, you can specify any Spark parameters that you want to be set on your context. So for example, we can set the Spark executor memory to be 4 gigabytes. So now, okay, an error. Yeah, I misspelled Spark executor here. 4 gigabytes. Okay. So when the server receives this request, it will spin a new process, and on that process, it will initialize a Spark context. As you can see, the context was created. Now we can go to the job section. Here you can see all the jobs that were finished or that are still running on your context. A nice cool feature is that you can see the error directly here if it failed, so you don't have to go through the log files. Also, you can see the output of the jobs. This is the output for the normalization job. And now let's run the download job. So you have to specify the full name of your class. You have to choose your context. And here you can enter any parameter that you want in order to customize your job. So the S3 download job was created with 3 parameters. The first parameter is the bucket we want to clone. So the S3 bucket, it's public. The second parameter would be the number of partitions in which we want our data to be parallelized. And the last parameter would be the output for this job. I didn't mention anything about this until now, because we want to stay in memory. We want to put our files in memory. So I will write to Tachyon. Tachyon is an in-memory file system about which my colleague Ema will talk later. So I have to provide a valid Tachyon path. This is similar to HDFS. You have to specify the master, the port, and the path where to write. Okay, now let's run the job. As you can see, the job have started, it's running. We can go in the context tab and into the Spark UI. And here we can see the stages that are run on top of our context. As I've said, you can go here on a stage and see the summary metrics for your stages. Okay, now if you don't like to use the UI, Spark Job REST also offers an HTTP client, which provides an abstraction on top of the RESTful layer, so you can go and write code in order to execute your pipelines. Now that the first part of the pipeline is over, I will let Ema continue with creating an in-memory data warehouse.
I'll go back to slides. Okay, so there are a lot of SQL engines that can run on top of data stored on HDFS. I could have used them all, but I chose SparkSQL. I chose SparkSQL because we're great fans of Spark, and because we invested in an open source project that submits queries on top of it. For those of you who don't know, SparkSQL is one of Spark's modules that is used for processing structured data. SparkSQL supports several input formats like files stored in Parquet or JSON, or data stored in Hive tables where the actual data resides on HDFS and the schema is in the Hive metastore. It also supports as an input already existing RDDs or data stored in external tables like Cassandra, for example, data that it's retrieved through JDBC. SparkSQL organizes the data into distributed collections called data frames, or the former schema RDDs for those of you who are more familiar with previous versions of Spark. We can work with it either writing code in Java, in Scala or Python, or we can execute SQL statements on top of the SparkSQL context. Okay, so the data of our pipeline until now was exported in CSV format in Tachyon, in memory. So in order to query it, we will have to create that abstractization, that data frame that I mentioned before. And in order to do that, we first need to have... Can I take this? Okay. We first need to have a Spark SQL context. And we will use this context in order to read the schema. I said that it's comma separated, so we will read the file from memory, split it after comma, and then map each field into a struct field that will create the struct type containing our schema. The data will be read in the same way. We read the data file, split it after comma, and then map each row inside your data file into a Spark SQL row that will be stored in an RDD containing rows. So now that we have the schema created and we have the row RDD created, we can create the data frame that we'll use to query, to have a look inside our data. So, in order to explore it, we can perform simple queries either directly using the methods built in upon a data frame. Here is an example of a group by. Or you can register your data frame into a temporary table and then execute SQL commands on top of it. However, this is not that easy to do. So you won't want to map your data into a data frame and then register it as a table each time you query, each time your Spark SQL context dies or you create a new session. So what would you like to do is to persist your tables somehow in order to share them across sessions. You have several ways to do that. Either creating a Hive table, executing a SQL statement on top of a Hive context. As you can see here, I have a Hive context. This actually extends the Spark SQL context and adds the functionality of operating with tables, with the data stored in Hive tables. Another way to share the tables between sessions is to save your data frame as a table, like here. What does this mean? A table will be created, a Spark SQL table will be created, having the schema stored in the Hive metastore. Okay, but we're building in-memory data pipeline. So the ingestion was in memory, the transformations were in memory. So what I would like to do is that my warehouse works with files stored in memory. What I like to do is save the data frame into a Parquet format inside Tachyon if possible. So I would be tempted to do this in the following way. However, this won't work. It won't work if the driver, the Spark driver, it's on a machine that doesn't have a Tachyon worker. It will fail during during writing the schema into the Parquet file. A colleague of ours open sourced an API that fixes this issue by sending the code that executes that writes the schema into Parquet file in Tachyon to the workers. So in the job I have created for exporting the files to Tachyon, I have used his library. You can take it from GitHub or you can download it from the Maven public repo because it's published. Okay, there are several file formats that we have used for different pipelines. However, we favor Parquet because being a columnar data representation format speeds up the aggregation queries. So for a long-running query, for queries that require only some columns, there will be read only the required ones and not the entire row. What's cool about it is that it supports nested data types, and the schema resides with the data, so you won't need an external metastore to store the schema for the files. Also, working with Parquet and with Spark SQL, it's nice because it supports schema evolution. So if you have some files in Parquet format having a schema and then you add another file that adds a new field, then Spark SQL will know to merge those schemas together. The most important feature, though, that I like about Parquet is that it supports efficient compression and encoding schemes, as they can be specified per column. If there is something that I have learned while working with files in memory, is that the footprint of your data, it's more important than the compression and decompression speed, because spilling files to disk, it will always be more expensive than a slower decompression algorithm. Of course, it depends on how large your data set is and how many memory you have on your machines. It's something you will have to balance, this battle between the disk I/O and CPUs. Okay, I have mentioned Tachyon. Tachyon, it's an in-memory file system. And what it's really cool about it is that it's not going to disk each time you want to read some data that you frequently use. It avoids this by keeping the data in memory. And the fact that the data is in memory makes it possible for Tachyon to allow different frameworks running on the cluster to access the same data set with the in-memory speed. Tachyon spills the data also to disk into a pluggable underlayer file system that could be either HDFS or S3, I don't know, GlassFS, whatever fits you best. There is another way to keep your data in memory. You could use Spark Cache for that. You could cache your tables, either calling the cache method on top of your SQL context, either calling the cache method on your data frame, or executing a standard SQL cache table command on your context. It doesn't matter which of these methods you choose, because Spark will cache your data in a columnar format in memory and will fine-tune the compression in order to minimize the pressure on your memory. So if we have Spark Cache, why using Tachyon? Well, there are a set of reasons why we like it. It's because sometimes Spark context might crash, and it does. It does, and if it does, you will lose your data from memory. And this means that you will have to cache once again your table, or you will have to trigger once again your transformations. And for large data sets, it's something that you won't want to do. So using Tachyon, you avoid this because the data will be outside your JVM, and outside your JVM, so you won't lose it when the Spark JVM will die. Generally speaking, Spark Cache will outperform Tachyon. And this is because while working with Tachyon, there is a time penalty inflicted by, I don't know, the serialization or deserialization or the calls between the two JVMs. But for long-running queries, Spark Cache will encounter GC. And if it does, your queries will be slower. This is something that you won't face if you're using Tachyon, because your RDD will be stored off heap. It will be in RAM disk. So in these situations, we have seen Tachyon outperform Spark Cache, but only, I have to say it once again, only when garbage collection kicks in, and this usually happens when your data is too large and there is a pressure on your memory. The most important thing why we use Tachyon is what I said before, that the data can be shared between applications with the in-memory speed. So you won't have to build a huge application to do them all. You can have microservices or micro apps to do several things and share the same data with the memory speed. Okay. Next, I will present one contribution we have made to the Spark ecosystem. It's Spark Job REST. It's a data warehouse that offers the possibility to concurrently and asynchronously submit Spark SQL queries. Actually, it's an alternative to Spark SQL JDBC, but it has an interactive UI, and it has a set of features that I will demo later on. JAWS has quite a history. I have been working on it since Spark 091. Back then, it worked on top of Shark. Now it supports Spark SQL, and you also can run Hive queries on Hadoop MapReduce. In future, we plan to support some other SQL engines that run on top of data stored on HDFS. This is the GitHub link. Okay, for resilience reasons, you might want to deploy JAWS on several instances and put it under the same load balancer. And thanks to the ACA actor system, these instances can communicate through each other, which makes possible a nice feature that we have, like query cancellation, meaning that it doesn't matter on which of these instances the cancel call ends up, the ACA actors will send this message to all the instances so that the context that triggered the query at the beginning will be the one that cancels it. Okay, next I will show the rest of the features directly in the UI to have a look to see how it is. The code that we used for this use case, meaning the download job, the transformation job, and the job that writes the files to Parquet, is available on GitHub at the following address. I will put this here to short demo. Okay. Do you hear me? Okay, it's okay. Okay, this is how JAWS looks like. This is how it looks like. We have here a query history. We can see the results. This is a quite cool feature that Spark SQL JDBC doesn't support. It's the retrieval of large results. What do? We take the results RDD, we zip it with index, and after that store it into Tachyon or HDFS if you want. And while retrieving the results paginated, we filter for that index in order to provide samples for the results. For a certain queries, you can see the logs. Here you can take a look into the Hive warehouse. You can see all the databases stored in Hive. For a database, you can see all the tables and, of course, all the columns for a table. Another nice feature that we have is the Parquet tables management. What does this mean? We map Parquet files from Tachyon or from HDFS into temporary tables in Hive and persist them across sessions. I know that this is a feature that the latest version of SparkSQL supports, but we needed it before, so we had to implement it. This means that if you are using Spark with an older version and you need it, you can use JAWS. Okay, what do we have next? There is a file browser that browses the files on Tachyon. This folder contains the output of the job that wrote the financial transactions into Parquet files. Okay, we can map this folder to a table. Oh. Let's say it's Buzz. Oops. Okay. Now the table was registered, so we should see it under the Parquet tables tab. It is here, and now we can query it. So let's say we want to select. I will write it with one hand. Select. Let's say count. All the transactions. Let's say that grouped by site from Buzz. Group by site. Awesome. Hope it works. Okay, you can see the logs and then the results. So this is JAWS. Let's see how Tachyon looks like for the ones who don't know. It looks just like a normal file system, but the files are in memory. Here is the Parquet format that I showed you before. If you go inside it, you can see that all the files are 100% in memory. Here you can see the underlayer file system. It's HDFS. And for each file, each Parquet file, you see the location, what's the IP where it's stored. Okay. Also, another nice thing, if you go in Mesos, we are using Mesos as a resource manager. If you go in Mesos, you could see that the SparkSQL context, the Joe's SparkSQL context, it's alive, can be queried. And if you look in the terminated frameworks, you will see that there is the context that wrote the data in Parquet in Tachyon. And this shows us that even if the context, SparkSQL context, is dead and buried, we can still query its output with the in-memory speed, and this is only because Tachyon. Okay, so here is the GitHub having the projects that we used for the use case. And here is the GitHub for Joe's. It's split in two microservices, one that triggers Hive queries and one that triggers SparkSQL queries. You have a README file explaining all the APIs, and also you have a configuration file to configure all the Spark settings you want in order to improve your queries. Okay, so thanks. If you have any questions for both of us, more than welcome.